So in Vcast 2 here, what we're going to be doing is looking at each layer of the sun, starting at the core and working our way out through the radiative zone, the convective zone, the photosphere, the chromosphere, and the corona, and just taking a quick look at each one of those. What's going on inside of them, what's important, and that'll be the Vcast. So first off, we're going to start in the core. Now, the core we've already talked a little bit about in the last Vcast because we know that it's really hot. All right, it's hot enough that, in fact, nuclear fusion is going on in there. And that means it has to be at least 10 million degrees Kelvin. All right. And it's so hot that it's actually in a state of matter known as plasma. Now, plasma here on Earth, it's not like a plasma TV, but lightning is a form of plasma. But plasma is like a gas. All right. It's most similar to a gas, but it's so hot that the electrons have actually been stripped off of the atom. And so you get this positive nucleus, all right, the protons, neutrons floating around in a soup, basically, of electrons. And it's very small. It's about 10%, I think, of the sun's total volume, but it's 90% of its mass. All right. In fact, it's so dense that it's about 13 times denser than lead, which would be 1.5 times 10 to the 5th kilograms per cubic meter, which doesn't mean a lot. But if you were to take two dice, size of the sun's core, and bring them to Earth, put them on a scale, what you would find is that they weigh somewhere between 2 and 3 pounds, depending on the size of your dice, which is pretty heavy for that size of material. And again, this is where hydrogen is being fused into helium. This is nuclear fusion. All right, extremely important. This is where the sun is getting its energy from. The conversion of hydrogen into helium, which takes a little bit of mass and turns into a lot of energy. All right, so that's where the sun's energy is produced. And again, it's being released as those photons. The next layer out is called the radiative zone. And what we want to talk about with the radiative zone is, first off, it is the biggest region. All right. And this is where energy that is produced in the core of those photons are being transferred away from the core via radiation. All right, photons of light. All right, and we'll do a little activity that describes this. But what I want to at least give you right now is that light that's being produced in the core here isn't just streaming out through all of this unaffected. In fact, it goes through what scientists describe as the random walk. All right, and we'll go through a lab and a demonstration of what this is and how it actually affects the light that is being produced in the core. All right, next layer out, the convection zone. Okay, convection zone, you should already know this process, or at least it should sound familiar. So we talked about convection when we talked about plate tectonics, that if you look at a lava lamp, the lava lamp has a bulb at the bottom that heats it up. And it heats that wax up so that it becomes less dense. And we know less dense things will rise, and then as they cool, it sinks back down. All right, in this case, it's not mantle material, but it's actually that gas. Hot gas expands and becomes less cool or less dense, rises, becomes cool, more dense, and sinks back down. And we can actually see this on the layer above, known as in a feature known as granulation. All right, this is what the surface of the sun looks like. And if you take a look at it, it looks kind of almost like it's boiling. And that's the idea here. That just like boiling water is that warm water rising up because it's less dense and then sinking back down. All right. We have the same process going on. So energy in this layer is actually being transferred through these convection currents. Hot gases rising up because they're less dense. And these little granulation spots, which don't look big in this picture, are about the size of Texas. All right, they don't look big because the sun is absolutely huge. And the dark regions around it are where that denser gas is actually sinking back down. All right, now getting into the atmospheric layers. Now, in the sun's atmosphere, the bottom layer is known as the photosphere. And this is actually the visible surface of the sun. In a few days, all right, or depending on when you're watching this podcast, we may have already done this, but we're actually going to go outside on a sunny day, and we're going to look at the sun's surface through special telescopes. Do not go out and just look at the sun because you'll hurt your eyes. Especially don't grab a pair of binoculars or a telescope and try it on your own. Okay, but this is the visible surface of the sun. This is where the light that we actually get from the sun, all right, leaves. All right. Then beyond that is a chromosphere, and the chromosphere, all we really want to talk about here is that the temperature is dropping. Now, the core is 10 million degrees Kelvin, and think of that as like a campfire. All right. If you're really close to the core, it's nice and hot. And as you back away from the campfire, it cools down. Now, the reason why I say this, all right, or bring it up here in the chromosphere, is that when you get into the last layer of the sun, its atmosphere, called the corona, which is only visible during a total solar eclipse, which is kind of cool to see. Something weird does happen, though. All right. It's at about 5,000 degrees Kelvin, but as you continue to go away from the chromosphere in the corona, it actually begins to heat up again. And it can actually heat up to 1 to 2 million degrees Kelvin. That's 10 to 20% the temperature of the core, which is very odd to think about. Think about going back to that analogy with the campfire. This would be like going away from the campfire, getting colder and colder, and all of a sudden, as you back away from the campfire, getting as hot as if you were right next to the campfire. Now, this is extremely odd to think about, and for a very long time, not many scientists knew what was going on here. But what I have seen and heard is that if you think back to those rising convection currents that act kind of like loudspeakers, all right, they are rising up just like a speaker pushes out air to make sound. Well, that compression actually can heat up the gases that it's compressing. And that's what I've seen as an explanation of these. So it's kind of a cool idea.